Okay, so what's going on in this one? We've got three people trying to move a heavy box. And first of all, just and my usual advice on stuff like this is skim through the problem to get a rough idea of what's going on, but focus on looking for what's the first time it actually asks a question. What's the first piece of information this is actually asking you for?
You mean just like the magnitude?
Yeah, specifically magnitude of Iris's force. So I think it tells us the direction. Actually, it doesn't tell us the direction. That's the next question, part B. But we want to find the for the magnitude and direction of the force provided by Iris. So let's take a look at the other forces acting on the box. In cases like this, we usually represent the object we care about as if it's just a single point. In this idea of a free body diagram or a force diagram. So if we just represent the box as just a point, because we don't really care where these forces are, we just care how much and what direction. So this point represents the box in what we're going to call a force diagram, in the sense that we're going to show the forces, or a free body diagram. Free body, in this case, the body is the box itself, just the object we're talking about. And when we describe it as a free body, we're saying we're looking at just that one object in isolation. We don't care about the other objects. We're just looking at the forces acting on that one object. So if we just list out all those forces, it looks like both Kyle and Carla are pushing on the box, or pulling on the box. And it tells us what those forces are. Kyle is pushing on the box with a force of 5 newtons in the eastwards direction. So for Kyle, we've got 5 newtons to the east. So that's the force of Kyle. I'm just going to call these, since we're going to get confused with F sub k twice. So let's just call this F sub 1. And how would we write that in terms of its components?
Would be 5, 0.
Yeah, 5, 0 newtons. So that would be the x and y component, since it's just 5 to the east and nothing at all to the north or south. We don't even need to use trigonometry there. We could use trigonometry. You could say this is, since the angle it makes with the x-axis is 0 degrees, you could say this is 5 cosine 0 for the x component and 5 sine 0 for the y component. But cosine of 0 is 1 and sine of 0 is 0. So it still works out to 5, 0. And what other force do we have here?
Force of Carla.
Yeah, and that's going to be 10 newtons, so twice as strong, at a different angle though, 30 degrees with the horizontal. So something like this. And we'll want to write that in XY components as well. Let's call that F2. And it's 12 newtons at an angle of 30 degrees with the horizontal. So let's take that aside for the moment. 12 newtons. And we want to split that into the X and Y components. An X component and a Y component. So we could call those F2X and F2Y. And we know that the angle between them is 30 degrees. So how would we find the X and Y components here? For instance, if we wanted the x component, what calculation would we usually use there? Yeah, we can use cosine. Oh, that is 10, isn't it? 10 newtons. Forgot about that. So yeah, f2x, we take the magnitude times cosine of the angle, because as long as you're measuring from standard position, measuring the angle from the positive x-axis, then the cosine will, the adjacent side will always be the x component. So 10 newtons times cosine 30 degrees. And likewise, y component is going to be the same, except with what change? Yeah, that'll use sine of 30 degrees. And sine of 30 degrees, if I remember correctly, is just 1/2, so that'll just be 5 newtons. And cosine of 30 is √3/2. So that'll be 10 newtons times √3 divided by 2, or 5√3 newtons. So those would be the x and y components of Carla's force. Meaning instead of writing it as 10 newtons in the 30-degree direction, we could instead write it as 5√3 in the x direction and 5 in the y direction. So that is Carla's force written in x and y components. In other words, eastwards and northwards components. Any questions on that so far? Let's go ahead and get a decimal approximation for 5√3 because we're probably going to need to add that to some stuff later. About 8.66. So we now have all the forces in that, or at least all of the known forces. We also have this unknown force from Iris. But what do we know about the total force here? Yeah, the net force has to be 12 newtons to the, and that'll have to be to the north. So 12 newtons straight to the north has to be the total here. So I'm going to draw that off to the side. This is not something you would actually include in the force diagram, because this is not one of the forces acting on the object. This is the total of all the forces acting on the object. So I'm going to put this off to the side as what all these values should add up to. However, we can get a rough idea of what Iris's force should look like before we even do any calculations beyond this. Because if we just want to say we've got 3 things that add up to this vector, how would you add vectors geometrically?
Wouldn't you know that you have to have some force going towards the left to balance out all the forces to the right?
Yeah, we are going to have a large amount to the left, or to the west, let's say, because we have a lot of force to the east already. And we know that the net force has no force, no east or west component at all. So those all need to cancel out. And yeah, algebraically, we would add up the x and y components. I think it might be useful to look at this geometrically first, though, just to get a visual idea of what this should look like. If you're adding vectors geometrically without even using the components, how do you add vectors together in terms of an actual diagram? Like if we've got vector f1 and we want to add vector f2, how would we put those together? Yeah, we could add those up tip to tail as usual. So let's try this. From some starting point, we add vector f1 plus vector f2 plus some unknown vector f3, and we need the result to add up to this f net. And generally the f net, the total force or total of all the vectors added together, is from the original starting point to the final ending point. So that means if we're adding f1 plus f2, but we want to get back to f net, we're going to have to add an f3 that's going to look like this. That way, F1 plus F2 plus F3 gives us the correct F net. So this is just geometrically, this is what we should expect F3 to look like. And of course, we'll want to figure out the components for that, but we can get a general idea of what we can expect it to look like in terms of overall direction. And note that, as you said, this does have to have a large westward component to cancel out the large eastward component we've already got. But this is what we should expect it to look like. Any questions on that so far? So let's put these back in the free body diagram format. We're just going to draw all of these force vectors as arrows coming out of the single point representing the box. So these are the three forces acting on the box. And let's add these together. We know that these have to add up to F net. We can say F1 plus F2 plus F3 has to equal F net. And you can split that up into two equations. You can say the sum of the x components has to add up to 0. So F1x plus F2x plus F3x equals F net x. And separately, the y components have to add up to 0. F1y plus F2y plus F3y equals F net y. So any vector equation, in a two-dimensional world, any vector equation is really two equations. In a three-dimensional world, it's really three equations. But if we take a look at just the x components, F1x is 5, F2x is 8.66, F3x is unknown, but we know they have to add up to 0 from F net x. And then you can solve for F3x. What's that going to have to be? The 5 and the 8.66 combined though. So what's 5 plus 8.66? Yeah, 13.66. Subtract that from both sides. We get negative 13.66. And I should include units here. That's newtons. So the x component is negative 13.66 newtons. And then what about the y components? We've got F1y is 0, F2y is 5, F3y is unknown. And they have to add up to not 0, but 12, because we do have a total force here. So if you solve that for F3y, what do you get? Yeah, 7 newtons. So we now know the x and y components of this previously unknown force 3. So if we label those, we've got an x component and a y component. And let's see what we can do with these. We know the x component is negative 13.66. And we know the y component is 7. So with those, we should be able to calculate, for example, the magnitude. How would we calculate the magnitude, the strength of that force? If you know this leg and this leg, how would you find the hypotenuse? Yeah, Pythagorean theorem will work well here. We can just take the square root of side squared plus side squared. And we can ignore that negative because we're squaring it anyway. So the square root of 13.66 squared, whatever that is, plus 49 is about 15.3. So that means Iris's force has to be about 15.3 newtons. And how do we find the direction here? How do we find this angle? Yeah, if we set this up on a, in fact, we could just set this up on the graph provided here. Let's try that out. I'm going to get rid of the F net vector because we now know, I mean, we've now figured out the important components we needed. So let me move these aside for the moment. And let's focus on that F3 direction. We know that we're going, do I have room for this here? Yeah, exactly. So let me scale this down. Let's switch to a different color. I think that's kind of difficult to see. So we know we have this vector with unknown angle, but we do know its x component and y component. We've got 7, and we've got negative 13.66. And there are a couple of different ways we could look at the angle here. Yeah, we want to use trigonometric functions again. Yeah, tangent will work best here because and I would use tangent because the y component we know with absolute accuracy, that is exactly 7. The x component, we rounded off a little bit, but it's still pretty close. The hypotenuse itself, we rounded off several times. So the hypotenuse is known less accurately than the other sides. So I would use the x and y components to do the calculation. One way to do this is to use this right triangle. And let's say we're trying to find this angle. To find this angle, we would say, like, let's say this is theta here. We could say tangent of theta is what side over what side? Yeah, tangent is opposite over adjacent, so that'll be 7 over, and if we're just treating this as sides of a triangle, I would treat the sides as absolute value. Ignore the positive and negative signs because the sides of a triangle are just positive numbers. They're distances. Then we take the inverse tangent. And let's see what that gives us. Inverse tangent, and make sure your calculator is in degree mode if you want degrees, or radian mode if you want radians. I'm getting about 27 degrees. And one way you would describe this, since this, if you imagine a vector pointing to the west and then rotating 27 degrees towards north, we would describe this 27 degrees north of west. In the sense that if you start off looking to the west and rotate 27 degrees towards the north direction, that's the correct direction here. So we describe this direction as 27 degrees north of west. Or alternatively, you could describe it from standard position. Standard position means looking at the angle as measured from the positive x-axis. Draw that a little better. So this angle here, what would that angle be? Or how would we find that angle? Yeah, that is 180 minus 27. So that'll be 153. So instead of saying 25 degrees north of west, we could say theta equals 153 degrees in standard position. Standard position for an angle means we're starting from the positive x-axis and measuring counterclockwise from there. So if you don't specify north of west or south of east or whatever, it's assumed to be in standard position. So we could describe this angle as 153 degrees. Any questions on that so far? And one other way you could do that, as long as you're talking about standard position, we could actually use the unit circle definitions of sine, cosine, tangent instead. If you imagine a circle centered at the origin, and this is going to be a bit of a mess. A circle centered at the origin there we go. A circle centered at the origin with a radius this way. The definition of sine and cosine and tangent in terms of a circle actually cover any angle, not just angles from 0 to 90 degrees. And in this circle, if you've got just some ray coming out of the center, intersecting the circle somewhere, the x and y coordinates where it intersects the circle are related to tangent. Specifically in the unit circle definition, tangent of theta is defined as the y coordinate where this ray intersects the circle divided by the x coordinate where the ray intersects the circle. So in terms of the coordinates, we can say y is 7 and x is negative 13.66. So we could write this as 7 over negative 13.66, including the negative, and then take the inverse tangent, which becomes negative 7 over 13.66. If we take the inverse tangent of that, inverse tangent of negative 7 over 13.66, the calculator actually provides a negative 27 degrees. And if you take a look at the negative 27 degrees on this diagram, we're measuring these angles relative to the positive x-axis. So this direction would be 0. And we're measuring it counterclockwise. So what would a negative angle mean? If the angle is negative, what would that suggest? What does it mean for an angle to be negative? By default, we typically assume that angles are measured counterclockwise from the positive x-axis. A negative value would just mean we're going going clockwise instead, the opposite direction. So negative 27 degrees in standard position would mean 27 degrees clockwise. So the inverse tangent function, if we include negative signs and positive signs from our x and y components and just treat tangent as y over x, we end up with negative 27 degrees, this direction here. So that is 27 degrees clockwise from the axis. Is that the correct direction for this vector? No, this is the exact opposite of the direction we're expecting. And the reason for that is inverse tangent or tangent functions are kind of ambiguous. The thing is, tangent is y over x. Y over x here could have been 7 over negative 13.66 or negative 7 over positive 13.66. If you take a look at the x and y components of this one, we've got positive 13.66 and negative 7. The calculator can't tell the difference between positive 7 over negative 13.66 or negative 7 over positive 13.66. It gives you the same result for both. So sometimes an inverse tangent function will give you an answer that's exactly opposite of what you should actually be writing down. So how do you fix that? If the calculator gives us negative 27 degrees, but we actually want this vector, how do you correct that? How do you rotate exactly half a revolution away from where you are now? If you have negative 27 degrees as the wrong angle, how do you flip that to get the exact correct angle? What's the difference between those? Yeah, 180 degrees. So we can take the negative 27 degrees that the inverse tangent function gave us, add 180 to get to the correct direction. So sometimes you need to do that. If you're calculating the angles based on inverse tangent of the y component over the x component, which should always work, but it sometimes gives you an angle exactly 180 degrees offset from where it should be. And that typically happens if your expected answer is on the left half of the y-axis. If you're on the right half of the y-axis, the inverse tangent function should give you the correct value every time. If you're on the left half, it'll give you an answer exactly flipped from where it should be. So you'd have to add 180. In this case, that gives us 153 degrees. And note that that's the same angle and standard position we were looking at earlier anyway. So either way, we get the same result, that the force exerted by Iris is 15.3 newtons at an angle of 27 degrees north of west, which could also be called 153 degrees in standard position. Any other questions on that one? And then it tells us that the force has been going on for some time, and that's the net force. So we don't actually need the individual forces for this part. Part C is looking at just the effects of the net force. So let me clear all this stuff. Because the net force was just that 12 Newton force we were looking at from the beginning. So if we have just a 12 Newton force, and I'm going to draw this smaller here so we have more space to work with. If the net force is 12 newtons, and we know that after some time, the box is now moving to the west. So we know V final is to the west. And we want to know which direction was the initial velocity. Any thoughts on how we could use the final velocity and the force to figure out what the initial velocity was? What does the force do to the velocity? Yeah, it changes it. And what equations could we use in order to figure out how much it changes it, or how those changes are related to each other? Yeah, we've got everything we need right here. The change in momentum is the impulse, or the total impulse. In this case, that's the total force times the amount of time it takes. The amount of time doesn't really matter here because it's a scalar, and we're just looking at direction. So that means the change in momentum should be in the direction of the net force. And then the times delta t is just going to be some scalar multiplier. But we should expect the change in momentum to be in this direction. So the delta momentum is going to be in the direction of the net force. Also, since momentum is mass times velocity, and mass is a scalar, we know that velocity is also in the same direction as momentum. So change in velocity is in the same direction as change in momentum. So change in velocity is going to be some vector in the same direction as change in momentum. And we can't really say anything about how big it is, but we at least know the direction. So change in velocity is in the same direction as the net force. And that should always be true. If you know the net force on the total force acting on an object, that direction is the same as the direction of the change in velocity. So we now know the final velocity, at least in terms of direction, and also the change in velocity. How could we use those in a vector equation to find the initial velocity? What's the usual relationship between initial value, delta, and final value? Yeah, delta velocity equals v final minus v initial. And if we want to find v initial, how would you solve for v initial here? How would you isolate v initial in that equation? Yeah, we add v initial to both sides and then subtract delta v. So that's really all we need to do here. And we don't have any numbers, of course, so we'll have to do this geometrically. But we can say that, let me move these aside. We can say that v initial is v final minus delta v. And we've got some options here. One way would be to add v final plus the opposite of delta v. Opposite of delta v would just be in the opposite direction. So same magnitude, but opposite direction would be negative delta v. So we could add these head to tail. V final plus negative v initial should equal, or sorry, v final plus negative delta v should equal v initial. So this then would be v initial. So it looks like if this force caused it to eventually be moving to the west, that means it was originally moving kind of southwest-ish. Not necessarily exactly southwest, but approximately in a southwest-ish direction. In other words, we had this v initial. We provided a force which caused a delta v in the northwards direction, resulting in v final being to the west. Because the delta v being to the north cancels out the southward component of v initial, leaving just a westward component. But of course, v initial had to have a westward component already, because a net force to the north can't change the east-west component. Any other questions on that one? All right, let me see if I can pull up another quick one that would be some good practice for this.
This is a more general question, but do you think that you'd be able to kind of like briefly go over impulses?
Impulse in general?
Yeah, and like how they relate to things.
Yeah, the main idea is that an impulse is just a force applied for some amount of time. So if you're just pushing on an object, you're applying a force. That force, of course, doesn't just happen instantaneously. It's applied over some period of time. So let's say you're applying a 50 Newton force to an object, and that force lasts for 3 seconds. If the force is 50 Newtons, and that needs a direction also, so let's say to the east, and the time it lasts for is 3 seconds, then the impulse, usually written as J with a vector sign, would be 50 Newtons times 3 seconds, so that's 150 Newton seconds, and that also has the direction to the east. So that means if you apply that 50 Newton eastward force for a time of 3 seconds, you're creating an impulse of 150 Newton seconds to the east. However, that impulse also acts as a change in momentum. If this is the only impulse, the only force of lasting some time applied to the object, then that means the impulse is going to cause exactly that much change in momentum to the object. And if you take a look at the units here, we got newtons times seconds. But what does newtons actually break down to? What does newtons mean? Do you know what is probably the simplest equation that force shows up in? Yeah, Newton's is just kilogram meters per second squared, because it's really just, yeah, exactly, a mass times an acceleration. This, I think, is probably the most, I guess, the most fundamental or most direct description of force. Apply a force to an object, assuming that's the only force or the total force, and you make it accelerate. The acceleration is going to be in the same direction as the force, because force and acceleration are both vectors. The amount of acceleration is going to be proportional to the force. The more acceleration you want, the more force you need to make that happen. And mass is the constant of proportionality here. So the more massive the object is, the more force you need to cause a certain amount of acceleration. And that's not to say you can't accelerate it at all without that much force. If you apply less force, you just get less acceleration. But generally, the more mass the object has, the more force is needed to make it accelerate at a certain rate. So mass is very usefully thought of as a difficulty level here. Mass is describing how difficult it is to accelerate the object at a certain rate. And if you take a look at the units there, mass is measured in kilograms, acceleration is measured in meters per second squared. So you get meters over second squared multiplied by kilograms. So that's the units of measurement for force, kilogram meters over second squared, since mass is in kilograms and acceleration is in meters per second squared. And we abbreviate that as newtons, because it's tedious to write out kilogram meters per second squared over and over again. But anytime you see newtons, if needed, you can expand that to kilogram meters per second squared. But we're also multiplying that by seconds. So for impulse, we've got force times time. That's newtons times seconds. But if you multiply kilogram meters per second squared times seconds, what happens? Yeah, we've got seconds in the numerator, because this is really times seconds over 1, and seconds squared in the denominator. So one of the seconds cancels out. We're left with kilogram meters per second. And kilogram meters per second is the unit of measurement for what? That's a mass, right? Kilograms times meters per second is velocity. What do we call mass times velocity? Yeah, that's momentum. Newton seconds is exactly the same as kilograms times meters per second. So impulse has the same units of measurement as momentum, because it's really just describing the change in momentum. We can say that the change in momentum is 150. Instead of Newton seconds, we'd write it as kilograms meters per second. It's the same thing. Newton seconds is the same as kilogram meters over seconds, but it's more useful to write it as kilogram meters over seconds in this context, because that's describing a change in momentum. And that also, of course, has a direction. It is a vector. So that means if you apply this much force for this much amount of time to the object, then the object's momentum will change by 150 kilogram meters per second to the east. And that's the change being added to whatever initial momentum it already had. So for instance, in a momentum chart, you'd draw this in the change in momentum column in the middle. If you knew that an object was experiencing this much impulse, then you'd fill in this much change in momentum in the delta P column, which might help you figure out how initial momentum and final momentum are related to each other. So that's the main idea of impulse. An impulse is a force multiplied by the amount of time the force lasts. And when you know the forces are balanced, in general, going back to this idea that the force equals mass, actually, before we do that, any more questions on the idea of impulse? Okay, so getting into force again. We know that and I should really say the sum of all the forces equals mass times acceleration. So what's probably the easiest amount of acceleration to be dealing with? What would be the easiest value of acceleration to analyze? Even easier than gravity. Because gravity is a constant value if you're on the surface of the Earth, which is convenient. But even easier than just some constant would be, yeah, no acceleration at all. So if the object is not accelerate, if the acceleration is 0, and let's take a moment to look at what that means. If the acceleration is 0, what is the object doing? Either not moving, or what else would be no acceleration? If the object is moving, but yeah, moving in a constant way, moving with constant speed, and also on what sort of path? What sort of trajectory would it have to be? Yeah, got to be in a straight line. Because if the object changes its speed, that's like getting faster or getting slower, that counts as acceleration. But also, even if it's going at a constant speed, but it's changing the direction it's traveling, that also counts as acceleration, because changing direction of travel is a change in velocity, because velocity is a vector. So any of those count as acceleration. If the object changes how fast it's moving, or changes which direction it's moving, or both, those count as acceleration. In order to be not accelerating, the object has to be maintaining a constant velocity, which might be 0. So either it's not moving and continues to not move, or it's moving at a constant speed in a straight line path. Those both count as 0 acceleration. In those cases, then we can conclude that, well, if the acceleration is 0, then the other side of the equation has to be 0 as well. So in general, if you know that the object is not accelerating, either it's staying still forever, or it's moving with constant speed in a straight line path forever, then you know that the total force is 0. That doesn't necessarily mean there are no forces. It just means that if there are forces, they all add up to 0. So this is generally what to look for. If you know the object is not accelerating at all, not necessarily forever, but for some period of time, then you know that during that period of time, all the forces acting on the object, if any, cancel out. And that gives you some useful equations. You can set up a free body diagram showing all the forces acting on the object, like we were doing with the box earlier. But you can assume that all those forces add up to 0. In 2 dimensions, that really gives you 2 equations, that the x components add up to 0 and the y components add up to 0. Total force, yeah, F net is just another way of saying the sum of all the forces acting on the object. Let me specify that. Net force means the sum of all the forces acting on the object. And that's just on one object, by the way, or on the whole system if we're looking at an entire system. But typically the sum of all of the forces acting on one object, not the forces caused by that object, but the forces acting on that object. And that equals mass of the object times acceleration of the object. So if you know the object is not accelerating, you know the forces have to add up to 0. And that's useful for setting up some equations to solve for some unknowns. But even if the object is accelerating, if you know how much it's accelerating, including direction, and you know the mass, you can say the total force adds up to mass times acceleration. So you can still get these equations. It's just made slightly more complicated by the fact that they add up to mass times acceleration instead of adding up to 0. But you can still set up the equations and solve as long as you know the acceleration. Any other questions on that? All right, sounds good. I will see you next time.
Thank you.
You're welcome.